Right, let's recap. When you have a capacitor, the capacitor charges up. As it charges up, you get a positive charge on one plate and a negative charge on the other plate. At V0, it becomes a maximum value of the potential across the plates. Plus Q across the positive plate and minus Q on the negative plate as you charge up the capacitor. If we set up the following circuit, we have our power pack at this position and our capacitor here. We have a voltmeter connected and a resistor. Now, when the switch is at position A, our capacitor will charge up to a maximum value. Once we move the switch to position B, our capacitor will discharge through the resistor, and the potential difference across the capacitor, which will be the same as across the resistor, is measured on the voltmeter here. Now, if we plot a graph of the discharge to the capacitor, the voltage against time, we will get this sort of an exponential decay curve, where the maximum value V0 is the maximum potential across the capacitor. Along the bottom axis we have time. We have time along the bottom axis. Now, as you can see, is the exponential decay value of this. So exponential is E values, but because it's a decay, we have to consider 1 over E. Before we look at exponential decay in a bit more detail, we'll have to look at something called a time constant. And time constant is a factor that gives us evidence on how the capacitor discharges. So T is equal to CR, where C is the capacitance value and R is the resistor value, or the maximum resistance value in a circuit. It's a simple equation, and the units for time constant is seconds. Now, you can do, I won't do it here, but you can work out the combined base units for C and R, and it works out as seconds as well. So just remember, time constant is a time value. Okay, let's go back to an exponential decay value. Now, if I take, remembering that time constant is CR, if I take the value of the CR here, now this is again simply done by multiplying the capacitor and the resistor in the circuit. Now, as I move up and I go across, I get a value of V. Now, this value of V here is actually 1 over E, the value of V0. So essentially, in your calculator, you put 1 over E times V0. So it'll be about 0.37 the value of V0, or 37% the value of V0. Now, if I take a value here of 2 CR, and I go across, I move across. Now, the value here, let's call it V1 for example. V1 will be 1 over E times 1 over E value of V0. Okay, and now we can do this for as many values of CR as possible. Just remember, the CR value is the same on that circuit. Now, since the voltage drops, the charge and current will also drop exponentially by looking at the equations. So here we can apply here the top value, Q0 is a maximum, it discharges exponentially. So if I take another value here of CR and go across, this will be 1 over E, the value of Q0. Okay? The same patterns occur with current against time. So this means whatever exponential log equation I can use for voltage, the same type of equation will be used for charge and for current. So this makes the maths a little bit easier. So let's go back to our original voltage treatment. So if I take my voltage against time, I get an exponential decay. Now, we're all happy with the CRs. So I'm going to try and work this out. Now, for any given value, say for example V here, we can apply the following equation. V equals V0 E, or exponential, minus T over CR. That becomes a constant value. Now, mathematicians among you will be able to work this out and why it's t, because that's the value against here, and CR is the constant value. Since it's an exponential decay value graph, we have a minus. So the same equation can apply if you're looking at charge. So Q equals Q naught e to the minus t over CR, and I equals I naught e to the minus t over CR. Now, you don't have to know how this equation came up from before, but it is quite a nice one to look at for those of you who are quite comfortable with maths. Okay, so if you go back to our original equation, V, let me write down here, V equals V naught e to the minus t over CR. We can rearrange this equation because if I take natural logs on both sides, we get the following. Log of V equals V naught minus t over CR. So if you have to work out the time value on here, we can work out time value or the CR value. Most questions come up asking either for C or R for the value here. Now, in a special case, okay, we have this. If V equals V naught over 2, therefore, we have V naught over 2 equals V naught e to the minus t over CR. Okay? So we can then